Now, my intuition tells me this is going to be a very beginner talk, so you guys stay engaged here. And with that, let's bring Richard to the stage. Now, Richard couldn't think of anything interesting other than a challenge that he has with his father, and he won't tell me what that challenge is, but I'm going to give him the microphone and we're all going to find out together.
I don't think I need a microphone for this, but my father's a minister, and he has certain powers, and he was always being curious whether I had inherited those powers. So let's try it. Well, looks like I have. There we go. Okay, there we go. Okay, well, I'm afraid he still holds the record for the numbers of people he can raise with his hands. But, okay, so today we're going to talk about the GoGC. It's going to come out in a month, in 1.5 in August. And we think we've got this latency problem solved for you, and that's what we're going to talk about. So before we go on, I want to talk about my co-defendants and my friends. This is the Cambridge runtime team. Austin, this is a new hire. He's a very big-brained type of guy. Sitting also next to him is Russ, who we heard about this morning. I'm Rick Hudson, and David Chase just joined us a few months ago. So that's the team. And sometimes we have discussions about the other Go, the Go you play with a board and little pebbles, and sometimes those discussions in this way, the discussions about the language are much more removed. So let's talk about making Go go. Okay. So we have this concept of a virtuous cycle. Okay, it's an economic term, and basically it says that if we write software, and the software will be written in Go, then our dream is that when the next piece of hardware comes out from one of the hardware companies, that software, unchanged, will run better. Meanwhile, since we have this new great hardware, we're able to write better software. And we're going to create this virtuous cycle where every generation of hardware enables a new, better generation of software, which just gets better with the next generation of hardware. And that ran in this industry for 30 years until about 2004. Because we all know, hardware people, they're still doing their jobs. They're putting 2 extra transistors in the chip, but it's not giving us 2 extra frequency anymore for good, solid physical reasons. But what we're noticing is if we've got more transistors, it's not translated into more cores, and Go is making a bet, more cores, better software. But the hardware folks will not put more cores in their hardware if the software isn't going to use them. So it's this balancing act of each other staring at each other. We're hoping that Go is going to break through on the software side. So long term, Go wants to reestablish or establish this new virtuous cycle. Okay? Short term, we need to increase Go adoption. A lot of things that Russ said this morning on doing this. The number one barrier at the low technical level has been GC latency. Mostly it's described by our users as the GC's too slow. But it's really the GC takes too much of the pause. Okay. About a year ago I was hired, and we said, well, how are we going to solve this problem? What are we going to do? And we're engineers. The first thing we did was we looked for a workaround. So maybe we can't solve that problem. We need a workaround. So let's go back to the basics. When's the best time to do a GC? Well, it's when nobody is looking. Okay? So we're going to put a camera on GC. We're going to look in your eyes, okay? And when you look away, we're going to do a GC. And we think that there's enough time when you're looking away to slip that GC in. Well, I'm not sure that's what Google hired me for. They had another project that was about to fail, you know. So anyway, so we can't follow their eyes. So let's distract them, okay? So the idea was to we'll pop up a network weight icon. We won't tell them what it is. We'll make them think it's the Wi-Fi. We'll stick weighting under it. They'll be happy as hell, you know. GC's not the problem. Okay, that's fine. But so those were the ideas. I'm not sure that Russ was approving of them, but we thought they were good. But the fact of the matter is, what we really wanted to do was, to be honest, we wanted to trade throughput for reduced GC latency. And I've had this ongoing discussion about throughput. And I'll just be real honest with you. We're going to make your program slower, not by much, okay? That's just a fancy way of saying that. But what we're going to give you is the number one thing you guys have been requesting, which seems to be reduced GC latency. And you'll see numbers further on showing how much we lost throughput, not actually very little, and you'll see great numbers for latency. So latency. Let's talk a little bit about the other half of this stuff, and that's latency. What is latency? And what is it? If you don't know what time is, it doesn't make sense. So what's a nanosecond? Grace Hopper, the great computer scientist, when I was an undergraduate, came and gave a talk at my college. And she gave me an 11.8-inch piece of wire. And she said, that's a nanosecond. Electricity, that's the maximum speed that electricity can travel. That is the same speed as light in a vacuum in space. 11.8 inches. And then here's a picture of her holding up a microsecond, 984 feet. That's how far light or electricity will travel. For 1 mile. A microsecond will travel for 984 feet, 5.4 microseconds, it'll travel for a mile. So you start talking about microseconds, you're talking about a very, very short amount of time. Okay? Get through the onion talk we saw this morning, to get to the outer onion, that's hundreds of microseconds. Okay? So let's talk about milliseconds, 1/1000th of a second. Okay? If you want to read 1 megabyte, only 1 megabyte, that's going to take a whole millisecond if you've got an SSD. If you've got the old mechanical stuff where heads have to move, for Christ's sake, well, that's going to take 20 milliseconds to read a megabyte from that disk. Now let's get into the human stuff. There's this thing that psychologists call perceptual causality. That basically says if you do something with this hand and you see something with your eye, you see it within 50 milliseconds, you perceive it as being caused by whatever you did. So if you move your mouse and the cursor moves in 50 milliseconds, you're happy as a clam. You figure that the cursor moving because you're moving your mouse. It takes more than 50 milliseconds, you do what I do. You shake your mouse thinking for some reason that's going to help it. Don't know why we do that, but everybody does. Okay, 50 milliseconds up. You ping something across the country, you ping something across Denver. Yeah, it's going to take about 50 milliseconds. How long does it take you to blink your eyes? 300 milliseconds. Okay, so now that we have a concept of what a millisecond is, let's see how much GC we can do in a millisecond. So the first thing we did, we said, well, let's look at Java. These guys have 20 years on us, okay? But Java's different. Java's different than Go. in a lot of ways, but I'm going to talk about how it's different to the memory system. First of all, we have thousands of Go routines. Java was invented in a time where you have tens of Java threads running on a single core. We have thousands of Go routines running on lots of cores. We use synchronization by channels. They use objects and locks. One of the big advantages, and I sort of thought to keep this on the slide, was that our runtime is written in Go. And that means that if the GC is causing the compiler problems, the guy in the next office comes over to me and says, the GC is causing the compiler problems, let's figure out how to fix it. Okay, if I was writing C, that would have been a problem. And that's what they're doing over in Java now. But the most important thing is that Go gives you control over spatial locality. So if you have some information and a bunch of backing store, like an array of floats, array of char in the case of a string, you can actually put those in the same object and allocate the memory form at the same time. That sticks these things together in memory. So no matter what happens to one part, it happens to the other part. And it's very valuable because now the programmer has control over that, where in the Java world, the Lisp world, the Smalltalk world, these would have been connected by a pointer. The garbage collector would be moving them around independent of each other, and that, as you can imagine, would cause all kinds of cache problems and greatly slow down your program. So the decision was, let's not go to Go. Let's build a GC for Go, the language Go, and let's get rid of this old stuff, and that's what we did. So, all GCs have certain things in common. So for people not familiar with GC, to make the rest of the talk work, I'm going to go through a couple slides explaining the phases of the GC. So we have our heap over here, which is a bunch of objects connected with pointers. But during the scan phase, we have to figure out what pointers allow the application to get into the heap. And these pointers are located in your registers. You direct access that way. Or in the backup of the registers, which is the stack. You get access that way. Or they're located in globals. And that's it. So if we know all the pointers in those locations, we know all the ways that the application program, or the application Go routine can get into the heap. We gather these things during something called the scan phase. So that's one phase. The next phase is the mark phase. Straightforward, we take the pointers we gather, we go to the heap, and so we do a transitive walk, and every time we run into an object, we mark it as being reachable from the program. And that's great. The GC, if it had control of the world, it would just stop all the application threads, tell them not to bother it, it was busy doing important work. But we want these application threads to continue to run. And they're going to run and they're going to start changing those pointers. And we're going to have to ask the application program to tell the GC, I'm changing a pointer. In this case, it allocates a new object and it creates a pointer to it. The GC had already marked that object as reachable. It'll never know about the green object. So in the mark phase, the program has to tell the GC to use something called a write barrier, okay, to inform the GC of what it's doing, and the GC has to take advantage of that and know about it. So, and that is more expensive inherently than simply stopping it and not letting it make those things. So these write barriers and this communication is what's going to slow things down a little bit. Okay, so the next phase, and that's pretty simple. We've got all the objects marked. We'll just run through memory, and if something's not marked, we know it's free, and we'll let the application program reuse that state. And on and on. So, one slide, this is what we do. Okay, we start off with this right barrier turned off. We are letting the application run as fast as possible. It has to check to see if the GC has been disabled. If it has, it just goes ahead and slams the pointer into the slot that it wants to. The check is in an hour-order machine. There's no dependencies. It'll just fly. You won't even notice that the delay will be very fast on modern hardware. At some point, we decide it's time to do a garbage collection. So at this point, we say, okay, before we scan these stacks, we're going to have to stop the world, stop all of these threads, or go to these, and get ready to do the garbage collection. So there's a brief stop the world there, and we're talking sub-milliseconds to stop the world there. That's a little. Okay, so you're going to lose a millisecond. Okay, then we scan the stack, just like I said, and that we can do while the go-to-keys are running. Okay, during that stop the world, we turn the right barrier on. So from now on, the application program can tell the garbage collector what it's doing. You then go through the mark phase. We mark everything concurrently, get the right barrier down so you see what's going on. When that's done, we want to finish. The mark has done as much work as it can, as possible. It's marked almost everything. It wants to coordinate one last time with the application programmer. So to do that, we have to do another stop world. Okay, we finish things up, we do some bookkeeping, we take care of finalizers, which is really a pain, but we take care of that and some other things. And when that's done, we turn the right barrier off. We don't need it anymore. We go to the sweep phase, and we restart all of the application scripts. And when that sweep's done, rinse and repeat. We're good to go. Okay, so that basically is the algorithm. We have references in the literature. Come get it from museum. And that's it. So let's look a little bit deeper into what's going on. I think you all understand this. Applications running along, it stops, and then all of the CPUs are used during the GC application gets to no time. GC finishes a little later. This is what 1.4 did, 1.3.12. Okay, on that. But in the new world, in 1.5, it's going to be different. Okay, we still have these big gaps where the application server runs no right barrier very much. Okay, but then when we do a right barrier, we have that bridge stop the world. That's your left goalpost there. Okay, typically a millisecond or less. And then we can go into the actual garbage. So we give the GC 25% of the CPUs. Okay, that's the lower blue bars here. And that's the GC working as hard as it can. Now, the evil application program can allocate a lot. Keep that in control. We actually ask it on allocation to assist the GC. So if you're not allocated, you're not going to be asked to assist the GC. And this is how we make sure that we finish the GC without having to increase the size of the heap. We just simply slow down the mutators that are allocated on using the resource we're trying to take care of. So, that's the algorithm. This is how it works. Let's get on to the slide of the show. This is the punchline. So what we have in the blue and the red is 1.4 and 1.5 latencies. These are seconds on the right-hand side. Those are gigabytes on the bottom. And as you can see, at 1.5, which is yellow, or orange, I guess, brown dots, they're right down there on the axis. Okay? So this is the slide that nobody thought. Let's show how close that is to the bottom.
garbage train, okay? Now I can drop that scale by 1,000x, okay? So this is 1,000 better on the scale, okay? So, and here we go. There's a couple of thousand points done here. As you can see, they're all pretty much below 2 milliseconds. A couple stragglers. The OS people say they could well be. My unit clock causing some of those. We don't know what they are, but we're not worried about it. You also might notice that there's a slope here. Okay, this is the value of having visualization. Okay, now we know what's causing that slope. We know how to fix it. We can fix it for 1.6. But as Russ said this morning, everybody has to play by the rules. We didn't figure it out until the 1.5 close date, and Austin and I weren't even going to bother to ask them. We do what the answer is. Okay, so that'll be fixed. So what's the cost? What can we do about it? Okay, so here's the cost. These are various numbers display and the benchmark we re-implemented from the JavaScript Octane suite because we didn't want to keep. And if there's a lot, on the far left, we have like a 50% increase in the heap size over line heap, which is well below about half what the default is. The second set of arrows up and down are what the default 100% is. But if you increase it to 200, a little bit beyond, you really start to get the actual cost, the throughput cost, down low. So these are throughput numbers. Sometimes, you do even better, for example, in JSON, it's even more dramatic, the drop-off, but then you start seeing which starts to get faster to get more. For single-threaded programs, it's great, because we don't stop single-threaded programs. We just let it keep on running. Want to keep the compiler guys happy? Tell them their compiler doesn't have to stop for a GC. It works wonders in the office. Okay. So, that's the story. Okay, this is what we're going to have for 1.5. So, this is a big lab for us. You know, it's a big deal. And we have to get this out to people. We have to start telling them that GC is not a barrier anymore. They can use Go. And we need to attract C programmers because we've got a better place for them now. And the reason they've always been using the GC was in their way is no longer true. Okay? In 1.6, we're going to be tuning for a sweet spot. But we don't know where that sweet spot is. We want it to be more predictable. We want things to be higher throughput. We want it to be lower latency. We know how to get the lower latency now. So that 1.6 work is going to be use case driven. And it's going to be the use cases of people in this room. So you need to talk to them. Okay? And I'm talking to some of you already. Pretty exciting. That will decide what we do in 1.6. And once we've done that, we can sort out we're going to increase Go adoption. And once Go demonstrates to the hardware people that it's the viable way forward, okay, and they're all on board with this virtuous cycle because they win just as much as we do. We're going to establish a virtuous cycle, and we're going to use Go to do it. And so that's it for the talk, and I'll take your questions.
Is the question about how the GC acts with different applications? Yeah. That's a scheduling question, which I didn't get into. Okay, so basically, we don't care about what's being allocated. We care about how much is being allocated, and we also care about what we saw the last time we did the GC, how many corners we had to go through, that kind of stuff. So it's really, we've got a feedback scheduler in there. So no matter what your program is, we hope that the scheduler will figure out when to start the GC, how much is this this to do and that. So yeah, the scheduler should be adaptive enough to deal with both kinds of programs or any kind of program. And that's a lot of what 6 work.
Hi, thank you. I wanted to ask how in your experiments did the new GC perform with large numbers of cores and given the scheduler using all these cores? Is there any variability with large numbers of CPU core?
I'm not sure I fully understood the question. Is it how the GC works when we increase the number of cores?
Yeah, when there are many routines spread out across many cores.
Okay, so if there's if you have thousands of Go routines and say tens of cores, okay, we keep track of whether we've already scanned the Go routine and whether it's changed its stack, and then we get the second stop the world down to the point of only stopping the ones that are running on the cores. Okay, so we're pretty good at that, and that technology was pretty much in there in 1.4. So we don't seem to be having trouble with large. We haven't tried 64 cores yet. Okay, but we're certainly not having any trouble with 32. Okay.
You mentioned that finalizers were a pain. Can you explain why they were a pain?
I'm sorry, can you repeat?
You had mentioned that finalizers were a pain.
Finalize.
Oh, finalizers, right. We have our finalizers sort of scattered and connected through each section of the heap. And if that flow that you saw there was actually us going through each section of the heap, seeing if there's a finalizer list on that spans header. Okay, and that's exactly what you saw. And as the heap got bigger, the finalizer got bigger. Okay, so yeah. Don't use finalizers. They're asynchronous and they fire when you don't expect them to. They're hard to debug. Anyway, I'm sorry, this slide.
Could you explain a little more what you mean by the assists, or the mutator assists that you see, the red area?
Okay, yeah. How does it mean by the assist? And so when the GC runs, when a mutator, when an application thread runs out of area, it goes back to the memory manager and says, give me another chunk of memory to allocate in. Okay? And at that point, we say, okay, you're asking for more memory. The GC is a little behind or it's not behind. If it's not behind, that's fine. If it is behind, it says, okay, you need to mark as much memory as you're going to take. Okay, so we make sure that marking progresses at a rate that guarantees that the heap will be completely marked by the time we reach the end of the GC. So it's marking work that we're asking the mutator to do. I think it's this slide.
Hi, this is really awesome. I want to ask, so as a containerized environment, we often hear a whole lot about keeping overall process RSS size. In the case of Go, we've seen fragmented heaps result in very large process RSS sizes, and they're totally built by compilers and whatnot. Is there any roadmap for action of the span of objects within the spans at all in Go's future?
I'm not sure I fully understand the question.
Heap compaction. Is there a roadmap for that?
Heap
Compaction.
Heap compaction. We've taken a different route. Okay, we followed stuff that had been learned in Horde, and then learned with Intel Scalable Malloc and TC Malloc. And what we do is we avoid fragmentation by allocating objects of the same size in the same span. Okay, so you can, as you can imagine, end up with fragmentation in this if you keep changing the sizes of the objects you're using. But by and large, we're betting, as the whole C community is betting, that they can avoid fragmentation using these techniques. So we're drawing from the C community to deal with fragmentation. And since those are the people we're trying to get to use Go, we're confident that they already understand and already know the tricks of how to avoid this. But that said, the current way we're doing some of this allocation can be greatly improved if we start picking up some of the stuff that has happened in the last 10 years in the sea world and dealing with Maui. That's how we're going to deal with that. We're not going to, never say never, but, compaction's not on our list for 1/6. I'll say that.
With previous Go versions, users had control over factors that affected the latency, such as the size of the heap, the number of objects, the number of pointers. With 1.5 and moving forward, what are the what can users do to control the remaining latency?
They have and I'm sorry, this is going to have to be the last question. You can catch me afterwards, I'll be right over here. They have one knob, okay? We looked at what some other languages did, where they can have hundreds of knobs and thousands of combinations, and it didn't seem at all the way forward. So we have one knob. It's the Go GC knob, and what you can do is that sets the amount of extra space that you can allocate in based upon, historically, how much live reachable data you have. Okay, so that's the one knob that we're going to give you. We're not going to have our Go programmers wasting their times twiddling knobs under the theory that something will get better and then it'll change at the next release. That's something some other languages do. We're not going with that. Okay.
And with that,